Hey, everybody. The main approach that mathematicians use to develop the logical and philosophical foundations of mathematics is set theory. Today, we're going to go over most of the building blocks of set theory, and this will allow us to be more precise in describing mathematical objects. Definition. A set is a collection of objects. The objects in a set are typically referred to as the elements of the set. If X is an element of A, then we write X in A. If X is in subset but not in A, we write X not in A. We say that the two sets A and B are equal and write A equals B if they have exactly the same elements. Writing this as a logical statement, we can say this as X is in A if and only if X is in B. Some general notation. We will almost always use capital letters for sets and small letters, either Roman or Greek, for elements of sets. There are some typical ways in which we might define a particular set. Let's say that we have a set U, sometimes referred to as a universe or a universal set, and we have a propositional function with domain U. Then we can define the set A, which is all of the x in U such that p of x is true. This will be the most common way that we define a set. This sort of definition is often called set builder notation. One example would be that we can define the set of perfect squares as the set S, where we take all of the integers such that x can be written as n squared for some other integer in n. We could also define the set algorithmically. For example, we might define S is n squared for n in Z. We could also define S using what's typically called roster notation by saying S is the set 0, 1, 4, 9, 16, 25, and so on. Of course, in this case, this is an ostensive definition. The hope is that the reader can infer the rule from the pattern. We also have some special notation for intervals of the real line. If we take any two numbers a, b with a less than b, then we can define four sets. A, b with closed brackets. This means all the points between a and b, and including the endpoints a and b. A, b with open brackets. This is all the points between a and b, but not including the endpoints a and b. We can also have the hapopen intervals, closed on the left, open on the right, open on the left, closed on the right. The rule to remember here is that the square bracket means that you include the endpoint on that end, and the round parenthesis means that you do not. We also allow for unbounded intervals with this notation. So for example, we can have intervals unbounded to the right, unbounded to the left. Some sets appear so frequently that we have special symbols for them. For the reals, we write the symbol R, but it's a kind of a fancy R with multiple lines. We use fancy Q for the rational numbers. Why Q? Because R was taken for the reals. We use fancy Z for the integers. This letter may not make sense, but in German the word for integers is Zahlen, which starts with a Z. Finally, we use N for the natural numbers or the positive integers. We say that a set A is finite if it has a finite number of elements, and we write absolute value of A for the number of elements. This number is called the size of A, or more precisely, the cardinality of A. If a set A is not finite, we say it is infinite. For example, the set 1, 2, 4, horse, cat has size or cardinality 5. We will assume the following axiom. A set exists that has no elements. We will call this set an empty set and denote it by this symbol, which can be written in LaTeX by \empty set, one word. Note that the cardinality of an empty set is 0. We also commonly refer to this as the empty set. In fact, we will show later that if an empty set exists, it must be unique. so it is proper to use the term the empty set here. If A and B are two sets such that every element of A is also an element of B, we say that A is a subset of B, written as such. Of course, if A equals B, then A is a subset of B. If we want to stress that A is a proper subset of B, i.e. A is a subset of B but A is not equal to B, we can use notation like this. Note that A is a subset of B is equivalent to saying that X in A implies X in B. From this, we can see the logical conclusion that A equals B if and only if A is a subset of B and B is a subset of A. In fact, most of the time when we want to prove that two sets are equal, we approach it like it's an if and only if proof. This might involve proving one direction and the other direction its converse. We might prove one direction and its inverse. Any sort of proof strategy that works for an if and only if style proof is the kind of strategy we'd use to show two sets are equal. Here's some examples of subsets. Recall earlier when we had a universal set U and defined A in terms of a prepositional function. So we say A is all the X in U such that P of X is true. This is implicitly defining A as a subset of U. Now let's consider the following example. Let A be the set of all real numbers X that satisfy X squared minus 4 equals 0. And let B be the set of all real numbers such that X squared is an integer. We can see that A is a subset of B, because if X squared equals 4, then X squared is an integer. Of course, the converse is false, and therefore B is not a subset of A, so that A and B are not the same set. We can generalize this example. If A is the set of all X in U such that P of X is true, and B is the set of all X in U such that Q of X is true, and P of X implies Q of X, then we get that A is a subset of B automatically. Even more generally, we can translate any statement about sets into a statement about prepositional functions and vice versa. You may recall a class activity earlier in the semester where we proved some logical statements using Venn diagrams, and perhaps it seemed a bit magical. But it's no magic, it's just using these ideas. We will develop this more in the next lecture. A third and very important example is when we consider the set of multiples of a number A. So let A be any integer, and we write the set A times Z, so basically A times the integers, as all the multiples of A. So that includes 0, includes A and minus A, 2A minus 2A, 3A and minus 3A, any number that's a multiple of A, any number that's an integer times A. Now here's a fact to ponder. It turns out that this is true, and we'll prove it, but AZ is a subset of BZ if and only if B divides A. Okay? Can you think about why this is true? Notice what's a little weird here is the order of A and B are flipped from one side of the if and only if to the other. On the left, A comes first. On the right, A comes second. So it is to say that larger numbers give smaller sets. Does that make sense? Does it make sense that 4Z is smaller than 2Z? Let that rattle around in your head a little bit. Now we're going to prove the claim that AZ is a subset of BZ if and only if B divides A. We'll prove from left to right and then from right to left. So to go from left to right, assume that AZ is a subset of BZ. This means that every element of AZ is also in BZ, because that's the definition of subset. And in particular, this means that A itself is in BZ. And by definition, that means that A is a multiple of B, and of course that means that B divides A. Now we go from right to left. Assume that B divides A. Then A is some multiple of B, so A equals KB for some K in Z. Now let X be any element of AZ. This means by definition that X equals A times L for some integer L. But since A equals KB, this means that X equals KBL, moving terms around, gives me KL times B, that's a multiple of b, and therefore x is in BZ. We have shown that an arbitrary element of AZ is also in BZ, and now we're done. Finally, we will now state a theorem with some facts about sets, some parts of which will show up in exercises later. The theorem says the following. Number 1. If A has no elements, then A is the empty set. Or said another way, if the cardinality of A is 0, A is the empty set. Number 2. Any two empty sets are equal. Number 3. For any set A, the empty set is a subset of A. Number 4. For any set A is a subset of itself. And then finally, number 5, if A is a subset of B and B is a subset of C, then A is a subset of C. The last one, number 5, is an example of what's called transitivity. And so we would say set inclusion is transitive. Okay, as I said, we'll prove some of these in exercises later. I'll stop there.